So I just want to give a little bit of a summary of lecture two. The lecture 2A and 2B is actually the first time I've recorded a lecture. So I personally was not very happy with them. And hopefully this will help things, clear things up if there were any questions as you were going through those lectures. So I'm going to give a quick note on frequentist versus Bayesian views of probability and statistics. I honestly, I'm familiar with Bayesian statistics, but only through, quick discussions in class, or I've worked with colleagues who consider themselves Bayesians. But in terms of wrapping my head around the very specifics, I'm not very knowledgeable in this area. So my understanding is very, very superficial. And so when I thought about what I mentioned in the lecture, in the recorded lecture, I realized that I confuse myself and therefore probably confuse all of you. So I just want to make a quick clarification at the beginning, and then we'll go over again, a statistics overview, and then we'll talk about descriptive statistics and inferential statistics. And then we'll move into a little bit of kind of very standard things that we would do in R, something that we'll do today in the exercise before we, move on to make our own script and that sort of thing. So all right, so my quick note is that in lecture two, I gave an example with Bayesian statistics and mentioned that, examples might be if you're watching Netflix, Netflix will suggest a show to you. And, if you're familiar with Netflix, sometimes it'll say, oh, 97% match based on, shows that you've watched previously. Or if you're shopping on Amazon, below it'll show you, these are suggested items that you might also be interested in, or and things that I think are growing to become very annoyed with is on social media when I get these ads. And I don't know if all of you have noticed, but you might be even talking with somebody in the room about something, and all of a sudden an ad pops up for something similar. These are not specifically examples of Bayesian statistics at work. It's actually examples of machine learning, but the concept is pretty similar, where you have information, you're updating it with, so you have a model, and then you get new data, and then you're updating that model given that new data. And that conceptually is also what Bayesian statistics is doing. So they're very similar. And in fact, Bayesian statistics can be used, their methods can be used to apply to machine learning, but the two are different. They're just conceptually very similar. So just remember, frequentist view of probability is that they're long-run frequencies, and we apply them to repeatable events. Whereas in the Bayesian view, probabilities are subjective. So it's the probabilities are the reasonable expectation of an event occurring based upon the data that we currently have. So I just wanted to make that quick clarification. Okay, so if you remember from lecture one, Dr. Armenta talked about statistics, and it's really just how we make sense of the world. Statistics has sort of two big branches. So there's descriptive statistics. And if you remember from lecture one, and I tried to emphasize it in lecture two as well, this is really the crux of a lot of the work that you'll be doing when you have your data sets for your project. It's really, really important to understand what your data looks like. And that's where descriptive statistics, comes in. So it's understanding, the distribution of your variables in your data set, looking at if your variables are distributed normally in your data set, do you have missing data, and what do the patterns of missingness look like? So those are all really important things in order to determine what kinds of analytic methods you would then use when you move on to then your inferential statistics. So inferential statistics are your tools that facilitate inferences about the unobserved population using your observable data, so using your sample data. And then within inferential statistics, we have estimation, and then we have hypothesis testing. So estimation, I'll talk about both more in detail, but very briefly, estimation is using your sample to estimate the population parameters. And then hypothesis testing is now really starting to look at differences and how does your population differ? Or if you are intervening and doing an experiment, does something change from baseline, and then now you've introduced this intervention, does it change from baseline to post intervention? Okay. So before I get into descriptive statistics and inferential statistics, we have to understand what is data. And it is funny because I Googled it, and a lot of the answers that I got were, they're a set of facts, which is actually not true, right? Because now we know that it's just a sample, and we're actually trying to use our data to get at the truth of the world. So, but I think in sort of, just everyday language, that obviously, makes sense, but in statistics, they're not the set of facts, it's just raw information or a collection of observations. And with that information, we're trying to get at the truth. Okay, so within our data, we have what we typically would call variables. So let's say I have a sample of 100 people, and I want to know their weight, their age, their sex, and maybe let's say, the amount of pain that they're having, currently. So those would all be considered variables. So in my data set, I would have people, and that would be the unit of interest. And then I would have a variable for weight, I would have a variable for age, for sex, and for pain. And these variables can be quantitative or qualitative. And I know Dr. Armenta discussed this a little bit, so I'll go into a little bit more detail. The quantitative variables are numeric. They can be interval or ratio variables. So the difference is our interval variables, we can interpret a difference, and there's no natural zero. So an example would be temperature in Celsius, right? So when we say it's 0 degrees Celsius, it doesn't mean there's no temperature. That is an actual temperature, right? So that's what I mean by no natural zero. And credit score would be another example where the range is 300 to 850. So there's no zero there either. Ratio variables, on the other hand, there is a meaningful zero. So if the value is 0, there means there's none of that. It's actually 0. So if there's a weight of 0, it weighs nothing. And for ratio variables, both differences and ratios can be interpreted. Numeric or quantitative variables can be discrete. So for example, the number of correct questions on a test. So what that just means is, let's say the number of correct questions on a test is 9 out of 10. There's nothing in between 9 and 10. So you can't get like 9 point. I get that some exams, maybe this is the case, but let's say for this example, you can't get 9.5 points. There's nothing in between that interval. So that would be considered discrete. On the other hand, numeric or quantitative variables can be continuous. So a good example of that would be age. So if someone is 20, and then, as time goes on, up until 21, you can actually divide, there's an age between 20 and 21. And even if you were to take that midpoint, 20.5, there's an age between 20 and 20.5. And you can just, all the way down, to the longest, decimal place, that there are values between the two values that you pick. And so that would be continuous. So on the other hand, we have qualitative variables. And these are also called categorical variables. You can have nominal variables in which there's no order. So for example, eye color or gender, right? Blue eyes aren't better than brown eyes, aren't better than green eyes, right? There's really no order, natural order. Men aren't better than women, vice versa. And on the other hand, there are ordinal variables, and these have some kind of natural order. So for example, education level. Not saying that any of these are better than the other, but you can see there's like a progression from high school, and then you move on to a bachelor's degree, to a master's degree, to a PhD. So there's like some inherent order in that variable. And categorical variables can only be discrete. Okay. And feel free to stop me if you have any questions. I'm going to pause. Okay, so three students just joined us. I apologize if you're waiting in the waiting room for a while. So we're just now doing a summary of lecture 2 and a little bit of lecture 1 as well. And I'm recording this, so I'll post it to the site so that you can watch the beginning of the lecture. But you've really only missed like a few slides. So, okay. So now that we've described data, where do data come from? And if you remember, Dr. Armenta talked about a sample versus the population. So our sample is drawn from the population of interest, and ideally it's representative of the population. And in statistics, all of our assumptions are based on us having a simple random sample of our population. That's not always true, and there are methods to correct for that, but everything that you'll probably read or learn about in this course is based on those assumptions, that it's a simple random sample of the population. And then again, it's often much smaller than the population. So if you remember from lecture 1 and 2, we talked about 2.4 million adults in San Diego, and then taking these smaller samples of 100 people and looking at our mean height and the distribution of sex in our samples compared to the population. The population is defined by the researcher, right? So it's really just the individuals or units of interest. So it's not necessarily people, but by and large in your research, you'll probably be, conducting studies and your unit of interest would be people. The population can be very broad, or it can be very specific. And I think the example was, they could be very specific, where they're competitive bodybuilders that you're interested in and you're drawing your samples from that population, or it can be much more broad, where you're interested in anybody who lifts weights at least twice a week. And remember, we typically cannot measure the entire population. And so that's why we conduct our studies using samples. And our samples are used to make inferences about the population. Okay, so remember, in statistics, we have descriptive statistics and we have inferential statistics. And in descriptive statistics, really our two main characteristics that we use to describe our data are measures of central tendency. And these include mean, and the median, and the mode. And remember, the mean is heavily affected by outliers or extreme values, whereas the median and mode are not as affected. They're very minimally affected by outliers. And then if you remember, just having an estimate of the mean, for example, just calculating the mean does say something about your data, but it doesn't tell you how much variability there is in your data. So remember, we had two curves, a blue and red curve, and one was very skinny, where there was less variability, and one was really, spread out, where there was more variability, even though they shared the same mean. So it's important when we talk about our data to also describe its variability. So measures of variability include our standard deviation, the variance, our range, or our minimum to maximum, and then our interquartile range. And that's just the middle 50% of our data. So what does it look like when we actually do our descriptive statistics? And you saw in our past 2 lectures an example of histograms, also an example of a box plot. And then this up here is just, the table here is just kind of what we refer to as a table 1. So it's in a sense like a histogram, right, in table form, where we take our variable, in this case, age, and we categorize age, and this researchers categorized it into 3 categories, and then we just look at the relative frequency of individuals within those categories of age. And in this case, they've further stratified it by whether that person was alive or dead at the end of the study. And then just, kind of maybe we'll talk about p-values later, but then they've also formally compared the age group. So whether there was a difference between these two. This part of the table is not, it is still a descriptive table, but this is getting now into hypothesis testing. So just ignore that. In fact, I probably should have just truncated that part of the table. But anyway, these are examples of visualizing our data, and we'll actually do that starting next week. Okay, so now we've talked about descriptive statistics, and remember the other portion of statistics, and I think inferential statistics gets a lot of attention, and it is important because that's the part where now we're trying to say something about the unobservable population with our sample data. So it is definitely important as well. But the first thing I wanted to do is kind of explain the difference between probability and statistics, and they're very closely related. And most courses in statistics, that are maybe for people who are interested in pursuing like a biostatistics degree, let's say, really start off with a heavy dose of probability theory before they move on to the statistics, because an understanding of probability theory is important for those individuals. This class is much more applied, and I'm very glad because I'm not super quantitative myself, and I think just giving you a little bit of an understanding is sufficient, and then from then we'll just move on to describing the tools that you can use for your research and when to use those tools. And so if that would be the biggest takeaway, I think, for this class, and probably much more useful. So what is the difference? In probability theory, the model is the truth about the world. It's known, but the data are not. So it kind of tells us, how often different kinds of events will happen in the future. So, we use the flipping of the coin example in lecture 2, the recorded lectures. So for example, in the case of a fair coin, our model is the probability of heads is 0.5. So we know that that's known, and that doesn't change. And remember, probabilities range from 0 to 1. In contrast, in statistics, we don't know the truth about the world, and that's what we're trying to get at with our data. So an example of statistics would be a friend tosses a coin and gets 10 heads in a row, and hopefully this example is familiar. We want to infer whether or not it was a fair coin. So remember, our model for a fair coin is that the probability of heads equals 0.5. That's the model, and that doesn't change. But if it's a trick coin, in which case probability of heads is not 0.5, I'm sorry, if it is a trick coin, then that model, p heads equals 0.5, isn't true, in which case the probability of heads isn't equal to 0.5. So in statistics, we have our data and we're trying to get at the truth of the world, whereas in probability theory, we know the truth. We have a model of the known model of the world, and we just don't know what the data look like. Okay, so if you remember from a few slides up, within inferential statistics, we have estimation and we have hypothesis testing. But really, to understand both of those, we need to talk about sampling distribution. And that's what I discussed, I think, in the second half of the recorded lecture 2. So if you remember, the sampling distribution of a statistic is the distribution of all possible values taken by the statistic. So for example, the mean, when all possible samples of a fixed size n are taken from the population. And it's just a theoretical idea. We don't actually build it in research. So, put another way, we take a sample from the population, we measure height, and we get the mean height. And then we take another sample from the population, we measure height, and we calculate the mean. So we do that over and over and over again. And then we plot the mean for each of those samples, and that would be our sampling distribution of a statistics, in this case, the sampling distribution of the mean. Okay, The sampling distribution of a statistic is the probability distribution of that statistic. So again, we take many, many samples of a given size n, and from a population with a mean mu or a standard and a standard deviation sigma. And if you were able to read the text, you could see when she's simulating, when the author is simulating a population and drawing samples from that, sometimes her sample means were above the population mean and sometimes they were below. And that's why there's a distribution. It still looks like a bell curve distribution, and that makes up our sampling distribution. So I talked about the sampling distribution of the mean. That was my example, and we'll see this over and over again. The mean is so important. So the mean and standard deviation, you're going to see this over and over and over again. And there are certain numbers that you'll also see over and over and over again in statistics. So, so now that we have the sampling distribution of the mean, remember, we can calculate the mean of that sampling distribution, but we also want to know the variability, right? So there is actually a term for it. The standard deviation of the sampling distribution is referred to as the standard error. And the standard error of the mean is just a special type of standard deviation, and that measures the variability in the sample distribution of sample means. And here is just the equation for that. So this is the standard error of the mean, and often, we can also just abbreviate it with SEM. And then in the numerator, we have the population standard deviation, and then in the denominator, we have the square root of the number of observations in our sample. Okay, so another way to describe it is it's a standard that describes the amount by which the sample means deviate from the mean of the sampling distribution or the population mean. And the errors, so the reason why we don't have just, zero standard deviation, there's error about that mean, refers to the fact that most samples are not exact replicas of the population, right? Sometimes, as I mentioned in the last slide, sometimes the mean is above the population mean, sometimes it's below. But with larger sample sizes, the sample means cluster more closely about the mean of the sampling distribution and the mean of the population, and that allows us to make more precise generalizations from samples to population. So put another way, what does that mean? With larger sample sizes, our standard error of the mean is smaller, and so our measurement is much more precise. Okay, so another concept that's really, really important and sort of the a foundation and really allows all of these statistics to hold is the central limit theorem. So what that proves is that the following three statements are true about the sampling distribution of the mean. So the first is that the mean of the sampling distribution, so that I'm denoting with mu sub x bar, is the same as the mean of the population, which is really nice. And if you remember in lecture 2, we gave an example of that, right? We had this mini population of 4, and we had possible values 2, 3, 4, and 5. And from that mini population, we took samples of 2, and then we plotted out all of the means for the 16 different possibilities for those samples, random samples of 2. And then we plotted the sampling distribution for those means, and we saw that in our sampling distribution, the mean was also 3.5, right? And the mean in our mini population is 3.5. So we saw that in that example, that the mean of the sampling distribution is the same as the mean of the population. And then again, as a standard deviation, the standard deviation of the sampling distribution, i.e. the standard error, gets smaller as the sample size increases. And then the other cool thing is that the shape of the sampling distribution becomes normal as the sample size increases. And that's true even if the population distribution isn't normal. So in the next slide, I'm going to give a visual of that. So here in this leftmost column, here in the top row, you see what the population distribution looks like. So in the very first column of the top row, we see a uniform distribution. And then here we have this bimodal distribution. And that just means the distribution has two modes or two peaks. And then here we have a very skewed, in this case, it's a right skewed distribution. So this is what the population distribution looks like. But when we start to take samples, and in the second row, we're taking a sample of 5 and then plotting the sampling distribution for those many samples of 5, you can start to see that the uniform distribution starts to look a little bit more like a normal curve, right? And then if you move on to the second column and the third column, you can see that those sampling distributions kind of shifting and looking a little bit more normal. And then finally in this last row, when we have a sample size of 30, so we're taking many samples of 30 and we plot the sampling distribution for the mean for those samples of 30, then you can see that now those sampling distributions look completely normal. So that's a really cool aspect also of the sampling distribution, that even if the population distribution isn't normal, the sampling distribution eventually with larger and larger sample sizes starts to look normal. Okay. How's everyone doing? Let me check at the time. Do you guys need a break or do you want to move on? I think I have maybe 10 more slides, 10 or 15 more slides.
I'm good.
Okay. All right, I'm just letting one student join. So I apologize. I'm kind of, as I'm going, I'm really focused on the slides, and I'm seeing that maybe some students got kicked off and are waiting to be admitted. So I apologize that you're waiting in the waiting room for a while. I'll get better as the semester goes on. I'll make sure to keep an eye on that. And then again, these are recorded, so you can always go back and look as well. Okay, so I'm just checking the chat. All right, thank you, Sebastian. All right. All right, so in inferential statistics, remember we have kind of two big ideas. We're thinking about estimation, and that's really just like a point estimate. We're just using our sample statistic to estimate the population parameter. Okay, and the other branch is hypothesis testing, and we'll talk about that in a few slides. So a note about the sample mean, it's an unbiased estimate. And I apologize, I'm introducing new notation here. I did not introduce it in the recorded lecture 2, but the sample mean X bar, which you've seen before, is an unbiased estimate. And when we talk about estimates, we give them this like caret top. So here, the unbiased estimate is mu with this little caret top. And so it's an unbiased estimate of the population mean. And remember, the population mean is just mu, okay? That said, the sample standard deviation, S, is a biased estimate of the population standard deviation. It's systematically biased, and in the textbook, and I should say, like, it's not necessary to read the textbook, but it's helpful, and I'm honestly finding it helpful, kind of refreshing my memory. But she actually showed through simulations that the sample standard deviation is systematically biased. What does that mean when I say systematically biased? So it's always either smaller or larger. So it's always, the error always goes in one direction. So in this case, the sample standard deviation is always smaller than the population standard deviation. So how do we correct that? And if you remember, when we calculated the standard deviation and made an adjustment, I think it was in lecture 1, and we probably talked about it in lecture 2 as well, made an adjustment so that we had an unbiased estimate of the population standard deviation, we divided by n-1. Okay, so the distinction here, this is the sample standard deviation, and this is the true standard deviation for our sample. And then to make it an unbiased estimate of the population standard deviation, we have this n-1. So we divide by the degrees of freedom. And I'll note too that when we do this in R, so the function is SD for the standard deviation, it will, R is smart, and the equations behind that function takes this into account, and so it will give us this value. Okay, so we have our point estimate when we estimate our population parameter, but we also in a lot of times we also calculate what's called the confidence interval. So this is on the left-hand side is just the normal distribution. And remember, and I probably didn't do the best job of it, but under this probability distribution, basically the area under this curve corresponds to 1. So under this would be 100%. And for a normal distribution, 95% of that area falls within plus or minus about 2 standard deviations from the mean. In this case, it would be exactly 1.96 standard deviations from the mean. So 95% of the area under the curve falls under these cut points. And I say 1.96, so you're going to see that number over and over and over again as well, especially when we start talking about hypothesis testing. So another way to put this is there's a 95% chance that a normally distributed quantity will be 1.96 standard deviations from the mean, and the mean being here in the very center. And this is true for a normal distribution. What does that mean for our sample? Well, there's a 95% probability that the sample mean, X bar, lies within 1.96 standard errors of the population mean. And so that I've just expressed by this, and it looks a little bit messy, but let's say this is the population mean, okay, and it falls within this range of our sample mean. Sorry, this should be a plus, so I'm going to correct that before I put the PDF up. This should be a plus, our sample mean plus 1.96 times the standard error. And then on the other end of it, we have the sample mean minus 1.96 times the standard error. So this is just a range, and that is called the 95% confidence interval. So this range of values has a 95% probability of containing the population mean. Okay, so when we calculate that, then we can say, okay, there's a 95% probability that the true mean falls somewhere in this range. And oftentimes when we report, we report results of our study, we don't just give the point estimate. We always give our confidence interval as well. Okay, but recall that the formula for the standard error of the mean, or SEM, is the population standard deviation over the square root of our sample, and we don't know the population standard deviation. So instead, we use sigma hat, and it's just this caret top again. That just denotes that it's an estimate. So instead, we use an estimate of the population standard deviation, and because of that, we have to use a t distribution instead of the z distribution. And that's just a little bit, the t distribution is it's a little bit more spread out, and it has heavier tails, and what that ends up doing is we end up getting a slightly wider confidence interval. But if our sample size is large, the t distribution starts to look a lot like the z distribution. And so then the confidence intervals are pretty similar. Okay, so one note about the confidence interval. We can't say there's a 95% probability that the true mean lies inside the confidence interval, right? So remember in frequentist statistics, we think of probability as something that we can apply to, it's a long range frequency, and it's applied to repeatable events. But the true mean isn't a repeatable event, right? It's the truth. It's sort of like our model. It represents the truth of the world that we're trying to get at. So we can't apply the probability to the true mean. So again, we can't say that with our confidence interval, there's a 95% probability that the true mean lies inside the confidence interval. What we can say is that there's a 95% probability that the confidence interval contains the true mean. And I know they sound really similar, but just to make a note that the probability in frequentist statistics, we're applying it to repeatable events. And that confidence interval is repeatable, right? So if we were to take a sample, calculate the statistic and the mean and the confidence interval about the mean, take another sample, do the same thing, and repeat that over and over, we have hundreds and hundreds and hundreds of estimates of the confidence interval. So that is repeatable. So we can say there's a 95% probability that the confidence interval contains the true mean. Okay, so we're going to move away now from estimation and go into hypothesis testing. So in hypothesis testing, and Dr. Armenta, he started to talk about it in lecture 1, and I know he didn't get to finish. So I've tried to put a little bit more slides here to go over it. And if it doesn't quite click, that's okay, because you know, in the coming lectures, we're going to talk about specific hypothesis tests. So as we start to introduce those specific hypothesis tests, you know, we'll revisit a lot of these concepts. So if it doesn't click right away, that's totally fine. And I find actually this is kind of one of the harder things for me to wrap my head around too, is understanding, you know, the theory behind hypothesis testing and even p-values. I think if you were to just ask me, you know, on the spot, you know, what does the, you know, p-value mean, I'd probably get pretty flustered. So, so really it's, you know, I'm kind of giving you a little bit of a foundation, and then really the big takeaway message is how to interpret your p-values, and maybe more importantly, how not to interpret your p-values. But if, you know, again, if this doesn't quite click, that's okay. The big takeaway is when we do hypothesis testing, you know, what is best practice for when you interpret the p-values that you get from hypothesis testing. And that's really what I want all of you to take away as you move forward and conduct your own research, because I think that's going to be more important than truly understanding the theory behind this. So, but I'll just cover it because it's still, you know, somewhat important, or I should say it's still important. So what is hypothesis testing? It just means that we have some theory about the world and we want to know if our data support that theory. And it can be expressed in 2 ways. So we have a research hypothesis, right? And that just suggests a specific relationship between 2 variables. So for example, your research hypothesis might be, does the new drug slow down the progression of Alzheimer's disease? And that's probably, those are the types of questions that you're very familiar with, right? A statistical hypothesis, on the other hand, proposes 2 competing statistical values. We have one, you know, our null hypothesis, and I'll describe that a little bit more in the next slide, where there is no difference in the mean cognitive decline between the treatment and the control group. So I'm not sure if you guys have taken like an epi class or talked about clinical trials. But oftentimes in studies, we have our test group, and then we have some kind of comparison group, especially in these experimental studies. So in this case, we have a treatment group and then our control group. And we're saying under a statistical hypothesis that the null is there's no difference. The alternative to that would be there is a difference in the mean cognitive decline between the treatment and the control group. And if you notice that second statistical hypothesis, or the alternate hypothesis, is very similar to this research hypothesis. Okay, so a bit of terminology for hypothesis testing. So there are a few elements of a hypothesis test, and I mentioned that in that last slide. So we have our null hypothesis, and that's just denoted by H sub 0. And it's just a statement regarding the values of unknown parameters. And typically we apply that we imply that there's no association between the explanatory, so in this example, the drug, and response, in this case, progression of Alzheimer's disease. So we typically imply no association between the explanatory and response variables in our applications. So we'll always contain some kind of equality. So there's no difference, or the 2 are equal to each other. The alternative hypothesis, and that's noted by H sub 1, is a statement contradictory to the null hypothesis. And so that will always contain an inequality. And then we have our test statistic. And And so maybe I kind of got ahead of myself. We talked about the Grubbs test at the end of lecture 2, and that was to test for outliers. And I referred to capital G as the test statistic. And so this is what I meant. It's just a quantity based on our sample data and the null hypothesis used to test between the null and the alternative hypotheses. So we calculate this test statistic, and then we look at, for example, a t distribution. And within our t distribution, we'll have these values, and I'll get into that in the next slide, where we can compare to these what they're called our critical values, and then we can, based on that, decide whether or not to reject the null hypothesis or not. Okay, so the last 2 elements are the rejection or the critical region. And so those correspond to the values of the test statistic for which we reject the null in favor of the alternative hypothesis. And then finally, we have alpha, and that's just the statistical significance. So that's the probability of rejecting the null hypothesis when the null hypothesis is true. And for most of our research, we are setting our alpha, and remember, Dr. Armenta really emphasized this as it's an arbitrary cutoff, but it's one that we use in research all the time, where we set our alpha to 0.05. Okay, so here's just, again, like a recap of the null hypothesis and the alternate hypothesis. So the null hypothesis, there's no effect, always. Always, the null hypothesis says there's no difference, there's no effect. Whereas the alternate hypothesis says, okay, well, the groups differ, and that could be in either direction. And that corresponds to our research hypothesis. And the way we can write that is as 2 mutually exclusive statements, and only one of these can be true, where the null hypothesis, so for example, the mean 1 is equal to mean 2, and the alternate would be that they're not equal to each other. So for example, in that coin toss, maybe because if we assume that a coin is fair, the probability of heads is 0.5. And so that might be our null hypothesis. And if we were to reject the null hypothesis, then the alternate hypothesis would be that p heads is not equal to 0.5. When we calculate, or when we conduct hypothesis tests, and we perform our statistics calculations, we get a p-value. Okay, and I know, I think Dr. Armenta did actually go over this particular slide in his first lecture. So the p-value tells us the probability under a specified statistical model that a statistical summary of the data, so for example, the sample mean difference between 2 compared groups, would be equal to or more extreme than its observed value. Okay, and this is why I say, like, it's for me, and it might not be for you, for me, it's really hard for me to wrap my head around all of this. But I think most importantly, it's key to say what the p-value isn't. And I have that down in red at the very bottom. So the p-value is not the probability that the null hypothesis is true given the observed data. Right? So remember, we can't apply our probabilities to non-repeatable or to fixed events. So again, it's not the probability that the null hypothesis is true given the observed data. So what it is, and I'll go back to that point just above that red statement, or the statement in red, the p-value is a probability of getting, sort of, for example, in another study, a test statistic that is more extreme than a one obtained if your study, if a series of assumptions hold. So it is strictly the probability about the data, not a probability about a hypothesis or about the effect of a variable. Okay. So when we're actually applying this, when do we conclude whether to accept the null hypothesis or to reject it? So the null hypothesis, if we fail to reject it, so we accept it, those correspond to large p-values. So if our p-value is greater than 0.05, typically we would fail to reject our null hypothesis. And then we would conclude that there's no difference between the groups. And this is where, P here, probability is greater than or equal to alpha, and we typically set alpha to 0.05. So again, if the p-value is larger than 0.05, we fail, or equal to 0.05, we fail to reject the null hypothesis. On the other hand, if our p-value is small or less than 0.05, then we reject the null hypothesis and accept the alternate hypothesis, and then conclude that the two groups that we're comparing are in fact different. And then this red line here, this alpha, is the line between large and small. So again, typically we set this to 0.05, but in other settings, we might make this alpha level smaller, or we might make it larger. But in probably almost 99% of what you do, you will be setting your alpha level to 0.05. And this is the basis for decision-making in statistics. Okay, so a few other notes. In hypothesis tests, remember when I said if we reject the null hypothesis and we accept the alternate hypothesis, it means there's a difference, and I had in parentheses, we can go in either direction. So that would mean it's a two-tailed test. But we also have in hypothesis testing a one-sided test, and that specifies the direction of the difference in advance. So an example would be that Grubbs test where we were looking at outliers, and the two equations for those test statistics were, I see a chat. Okay, so I'll hopefully it will make a little bit more sense. Someone asked, this part always confuses me. So I empathize with that. So hopefully this will make it a little bit clearer. So remember in the Grubbs test, I said these are the test statistics. This one is to see whether this outlier is larger than the max. This outlier is larger than not the max value. What am I trying to say? Let's say we have a distribution and we have two standard deviations from the mean, or more extreme would be 3 standard deviations of the mean. Is that outlier more than, for example, 3 standard deviations from the mean? That would be a one-sided test because we're specifying just one direction. Is it larger than that top end? Or on the other hand, the other equation for the test statistic I gave was, is this value, this observation, is it less than 3 standard deviations from the mean in the opposite direction? So is it smaller than that last point there? So that is an example of a one-sided test. And so we'll often see, is it greater, is it longer, is it increased, or is it smaller? So there's some specification of direction for a one-sided test. For a two-sided test, on the other hand, it just means there's no difference between the groups, and the direction doesn't matter. So we just say they're different or they're not equal. By and large, in medicine and in the research that you do, we are rarely certain that we would expect a value to be larger or smaller. So we often don't know the direction of any effect in advance. And so by and large, you'll be implementing two-tailed tests. Okay, so here's just a visual where we have our Z distribution, and this is just a normal distribution, and this corresponds to a non-directional hypothesis, right? And so you'll see this over and over again. So this is the 95% of the area under the curve. And this region here between 1.96, negative 1.96 standard deviations from the mean and 1.96 standard deviations from the mean in the other direction, if our value falls within this region, this corresponds to the null hypothesis. Okay, but if we get, so remember alpha, we typically set to 0.05, but in a normal distribution and in a two-tailed test, we have to divide that 0.05 into 2 sides. So on either side of this distribution, we have 2.5% or 0.025. So it's just alpha divided by 2 on this side, and then we have alpha divided by 2 on this side. So this area, this is the critical region, this is the rejection region, that corresponds to the alternative hypothesis. So this is the region where if we get a p-value of less than 0.05, we would reject the null hypothesis in favor of the alternate hypothesis. Okay, so sometimes, but not often, right? So by and large, you're going to be doing two-tailed tests, but sometimes we might review the literature, and then based on the existing literature, there's a strong suggestion that maybe there is a difference, and that difference is going to be in one direction. So if you know to expect the mean of one population to be larger than the mean of another population, and then the full 5% of alpha can be placed at one end of the normal curve. And what does that look like? So that just looks like this. So now in this case, we don't divide alpha by 2 because it's all lumped together on the right side of this distribution. So all of this corresponds to 5%. Now you have on this side of the distribution, your null hypothesis that mean 1 is greater than or equal to mean 2. And then if your p-value falls within here, then you reject the null hypothesis in favor of the alternate hypothesis where mean 1 is actually less than mean 2. Okay, and so then the flip of this would just be, if you were interested in a null hypothesis and mean 1 was less than or equal to mean 2, you would just have your critical region or your rejection region on this side of the curve. Okay. So one last note on p-values. Again, they give no indication about the clinical importance of the observed association. So I can't remember the exact example that Dr. Armenta used. I think it had to do with running time. So let's say, you implement some training regimen and, a run time for a mile increases, in your test group by 0.0001 seconds, and you get a significant p-value. That's great. It's statistically significant, but in practice, it's maybe not that important, right? The difference, I would say, oh, that's not a huge difference, a change in their mile time. And then again, a large study may result in a small p-value based on a small difference of effect that may not be important when translated into clinical practice. And so one of the things we have to be really careful about, and this is actually true for the study that I work on and Sabir works on, we have 200,000 participants. So whenever we look at descriptive statistics and compare our different groups, and also when we run, certain models using our data, it's such a large sample of individuals that we often do get significant p-values. But for example, the difference might be, oh, well, there's, 50% men in this group and there's, 50.2% men in this other group. And when we compare them, we get a significant p-value. But I would say, there really isn't a, meaningful difference. That distribution, 50 versus 50.2% really isn't that meaningful. So therefore, it's always important to examine the effect size and the confidence intervals. And that goes back to estimation. Okay, so I'm gonna stop there in terms of the, the kind of statistics recap. And then in the next slide, I'm just gonna give like a quick overview of some of the things that you will be using in R today. Okay, so some basics. So just remember the order of operations. We're in our getting familiar with R, we're going to calculate, total monthly salary. And so just a reminder, our parentheses come first, then our exponents, then multiplication and division, and then addition and subtraction. So you can write out your equations and use parentheses in R. You can use this, caret to denote an exponent. So these all correspond to your operators, okay? So plus, minus, multiplication, division, and then exponentiation. Oh, okay, great question, Amanda. So should we open up R now? Yes, and I'm curious to see how this will work because let's see, maybe just wait a second. I'll go over this slide and then I'll open up R and share my screen. And then, so that might be a good point actually to start R. But if you want to just open it up now, that's totally fine. We're going to go over it in a second. So I'm just going to finish this slide, and then I'll also open up R so we can kind of follow together. Okay, these are examples of functions. So some functions that we might use throughout this course. This is for square root. This is to round a value. This is to take the absolute value, the mean, and the median. Okay, so there are also arguments of a function. So when we round a value, so if we were to put in here 3.1415 or just pi, the result would be an integer. So I believe the R would give us just 3. But if we want to say, please round it, but to 2 significant digits, then we would include an argument in our function. So in this case, the variable is pi, so 3.1415, and then we would specify digits equals 2. And then that, in effect, would give us 3 to 2 significant digits. So R would then spit out 3.14. Okay, and if you remember, a package in R is just a collection of functions and sometimes like data sets, for examples, that you can go through using those packages, and they're all just grouped into one collection. So for example, ggplot2 is a package in R, and that contains functions to plot data. Oh, excuse me. Okay. I ended my slideshow, sorry. So, but that last line was, I don't know if you noticed when you opened up R and then you closed it out, it asked you if you want to save your workspace. My personal opinion is to not save your workspace. And this is why. If you say yes, R will designate some folder, and it's probably on your C drive under program files, where it will save variables that you've created, data sets that you've created, and pull up code that you've created. And when I open up R, I'll show you, remember when Dr. Armenta opened up R, in that right upper hand screen, it shows you kind of historical lines of code that you've run. So yes, it can be helpful. So obviously, this is completely at your discretion, whether you want to save your workspace or not. For me personally, I find that it's best practice to save the code that you write into a script or a separate, a separate file, and then also save any data sets that you've created or are using for your analysis into a folder that you specify. And then when you use R, you can point to that specific folder and pull any code or data sets that you've used for that specific project. So it just gives you a little bit more control over where all of the work that you're doing is being placed. So for me, I like to just clear everything so that when I open R again, I start with a clean slate. And if I want to go back and look at code that I've used, for example, then I would just open up this, the script that I saved. So that's just me, but I can also see where, saving your workspace would be very helpful, because then you can access a lot of these things sort of automatically. So I'm going to open up R now. So everyone, if you are ready, you can do the same. Yes. Yes, so someone asked, clear the environment and packages. So yes, I believe once you install the packages, they're installed, you would just need to load them when you open up R again. Okay. So I've opened up R. I'm going to start sharing my screen because I think let's see. Let me find it. I have lots of things open here. Okay. All right. Can everyone see R? Okay, awesome. Let me see, check the time. Okay, so we've been going on for an hour. So I would say, let's take a 5-minute break. And during the break, you can open up R, say something if you're having trouble opening it up. Yes, ideally, we should be using RStudio. You don't have to. In fact, I typically use just R, and you can write scripts in just R, but I think R Studio is really nice because you can see sort of everything all together. Your directory with all of your folders. You can see your script in its own window, and then any history in that upper right corner. So it's actually just a lot more user friendly. I feel like. So let's take a 5-minute break. And I'm just going to go through comments, and if you have a question. Oh, okay. So if you're using RStudio, that won't be a problem. Yep. Totally fine. Totally great that you've been using it. Oh, okay. RStudio won't open. Okay. So Amanda is, does it just like won't open at all? So it's okay if we use just, let me see if I have I would say if you're just using R, okay, so show me what it says. If you're just using R, you can still write a script and save that script, and then still highlight, code in your script and run it. Oh, interesting. Okay, so this app won't open on your PC. That's interesting. Okay, maybe if for today it probably won't matter too much, but actually I do think it will make it difficult for you today, because some of the things that we're doing in the exercise do use things that are specific to RStudio. But the general idea today really is to just kind of move around in R. So kind of like the basic things that we're running, you can run in both R and RStudio. Okay. If you still have issues, and again, I'm still not in CSU system, so I will post on Cougar courses. My tech skills are very limited too. So this is why I'm not very helpful right now. I will post my email address, my iCloud email address, then you can email me through there. And then once I get the CSUSM email up, everyone can start to email me at that email, but I realize that I'm sort of out of reach right now. Okay. Oh, okay. So Sebastian, what do you mean by screen share? Are you guys able to see my screen?
Oh, no.
Or are you asking Amanda to share?
Yeah, I was saying that she can screen share and we could walk her through it.
Okay. Do you guys want to do that now?
Because I had such a hard time.
Did you?
Yeah, it was so complicated.
Okay.
I had no clue what I was doing, but I got it.
Okay. Do you have a Mac?
I got it. Yeah.
Okay. You have a PC, Amanda. Okay. I'm on Zoom from a laptop and using my PC. Oh, okay, right. That's right. I remember now. You have a laptop and then you have a desktop that you're working off of as well. Okay, okay. Would you be okay with us just kind of walking through this exercise? And then I definitely want to see if we can set you up with RStudio. And if that means like it's not like good social distancing practice, we can meet and I can try to help you kind of set that up. Oh, I'm sorry, but it's on your desktop. We will figure something out. But I also want you to know that if you can't end up, if you don't end up using RStudio, that's okay. Everything we do in RStudio, we can also do in R. It's just not as pretty. So rest assured that it will not hold you back from doing all of the things that we'll be doing in class. Okay, awesome. That's super helpful. Okay. All right, so I'm going to, let's see, how do I do this? So one thing I noted right at the beginning of class is I just also have my laptop. And so trying to view the exercise at the same time I'm looking at the document, getting familiar with R is a little bit challenging. So I'm gonna see if I can move this over. Okay. Does everyone have getting familiar with R open so that they can look at it while we're working in RStudio? Okay. Okay. If this is a problem for you, if there's an issue where you're not able to look at the exercise while you're working in R or RStudio, please let me know. We will figure something out. Again, I'm happy to just print it out for you, the exercises, and mail them to you if necessary, because I know none of us really have access to, we don't have access to Canvas really, or some of the, some of the tools that we typically would have. So like I don't have a printer at home, for example. Okay. So when you open up RStudio and you can see in my screen, you just see the console. You don't see that upper left-hand quadrant. Yes, okay, they are on Cougar Courses under week 2, and they are also in Cougar Courses under the exercise link. So, yes, so they are, that's where I place them. And that's where I will place, so the exercises in the future, I'll place them all in that exercise section, but I'll also post them in the weeks that correspond, during which we'll work on those exercises. So, so yeah, if you want, we can wait, because honestly, this part won't take that long. So if you want to go ahead and, we can wait while you open that up. And then as you're doing that, I'm just going to explain here in my screen, you can only see the console area. Okay, awesome. And then on the, when Dr. Armenta showed you, and in my R video, there's that upper left-hand screen with the source area. So we'll open that up in a sec. But first, in that console area, just practice using it like a calculator. So we kind of did that. And so in that getting familiar with R document, it says type 2 + 2 and just see what happens, right? Oh, and now I'm connected to there, okay. And that gives us 4. Okay. So then the next, the next thing is make sure you can add, subtract, multiply, divide, and take powers, as well as using parentheses if you want. So for example, if I were to add 1 + 2 times 4, R knows the order of operation, so it's going to multiply 2 and 4 first to get 8, and then add 1 to get 9. Okay. But if I wanted to add 1 and 2 first, I would just use my parentheses. So then I would get 3 times 4, and that would give me 12. Okay, so you guys can do that on your own. And then once you're ready, what we're asking you to do is, suppose you're interested in calculating how much you'd earn in a month at a new job. The job pays $25 per hour, and you will work 15 hours per week, but you're taxed at 20%. So how much money after taxes will you have at the end of 1 month? And in this case, let's just assume that 1 month is 4 weeks. So using the console like a calculator, let's calculate your answer. So I know this is the tough part, is I can't see everybody else's screen, but just let me know if you're having issues. Okay, so we have a job. It pays $25 per hour. Okay, and you're going to work 15 hours a week, but you're taxed at 20%. Okay, so, okay. And then at the end of 1 month. So this is all going to happen in 4 weeks. So $25 times 15 hours per week times 4 weeks, and then we get taxed at 20%. Give us $300. And so sorry, I'm having tech issues here too. I'm just trying to scroll up on my exercise. Oh, I'm sorry. Okay. I made a mistake. This shows you like even basic, very elementary math sometimes is an issue, So we get taxed at 20%, which means you end up with 80% of what you've made. So it should be $1,200, much better. Okay. All right, so the next thing on the exercise, it says use the assignment operator. So remember in the example video for R, we created an object. And here in this exercise, we're creating an object called monthly wage. And so now we want to use the assignment operator to store our answer. So what does that look like? So we would write monthly wage, okay? And there's the assignment operator. And then here we would write 25. Okay, so now we've stored it. It doesn't show us. And then if you look here in the global environment, you can see that object that we just created. Okay, and then if we wanted to just look at what's the value of monthly wage, we can type that out and we see 1,200. Okay, so the source area in R is also known as a script editor, and that's one thing that's not popped up on my screen just yet. It's just a source where it's a place to store multiple lines of code. So if we were to actually conduct an analysis, typically we would have many, many lines of code, sometimes hundreds of lines of code, and it would be really onerous if we were to do it just from the console. And so that's where a script is really helpful, because then it's just one place where we have all of our code and we can either run it all at one time, or we can select certain lines of code and then, and run it in pieces. So typically most of what you'll do is in that source area. So the first thing we're going to do is create our script in R. And so, Amanda, this is where you won't have to do this part. When you do get RStudio, then you can go through the rest of this exercise. But basically, this is kind of opening up a script and creating it. It's not difficult. So, and then if you have any issues with it, once you get RStudio, just let me know. And I can even make a video for you if you want and send that over. I can post that to Cougar Courses. So just let me know. Okay, so everyone who is in RStudio, we're just going to go to, and now I'm having like tech issues trying to actually navigate. Yeah, okay. All right, here we go. Now I'm back in. Okay, so click File, and then New File, and then you're gonna select R Markdown. So this, I think, as I mentioned, I'm typically used to using just R, and I normally would just open up an R script. So this is actually new to me. So we're gonna open up R Markdown. Okay, I don't know if that did anything. Hold on, okay. My computer's just slowed. You see my little ball going? Okay, I think, okay, all right. So now it's saying, all right, it requires updated versions of the following packages. Do you want to install those packages now? Yes, because I can't move forward unless I do that. So I'm gonna go ahead and do that. You guys might get that pop-up window as well. Okay, so now it's just installing all of these packages. Okay, so this is where I kind of want to pause and ask everybody, what do you think would be most helpful? So I know it can be hard, like if you're trying to work in the R environment and I'm also working in the R environment to kind of show you as I work through these exercises, you're basically split, right? Between looking at my screen and looking at your screen. So I don't, maybe that's helpful, maybe it's not. So I think this is, as I'm installing all these packages, I think this is where I kind of want to pause and ask everybody, what would be your preference? So the idea kind of going in was I would record lectures that you could watch before class, and then give you like a mini recap at the start of class. I know my mini recap ended up being quite long, so it was like an hour today. And that I would say, maybe typically a lecture would go like an hour, maybe an hour and 15 minutes. So the idea anyway was to record the lectures and then give this mini recap and then spend most of our time working in R, so that if you're working on R on your own through these exercises, you could ask me, in real time for help. And so that's one way to do it. But as I said, it was really hard because as I, giving these lectures, I don't know if everyone's sort of like catching everything as I'm going along. So the other option then is to spend, the first half or, or a little bit extra on giving the lecture, and then a little bit of time where maybe I show you a little bit of how to, maybe we go over the first few questions of, subsequent exercises. And then kind of I can give you an idea of how to work through those exercises and how to think about them. And then separately, I can create videos of R where I'm going through. So for example, next week, we'll start to do some descriptive statistics, and I can do, I can record a video where I am calculating a mean and a standard deviation, plotting a histogram, for example. So I don't know, like, and we all don't have to decide now, but let me know, what you think would be most helpful. So, okay. Okay, so there's one vote for live help with R.
I was going to say the opposite. So it'd be like recorded R and then live lecture.
Okay. Does everyone else have any recorded R? Oh, I see. Okay. Okay. What I'll do is okay, so you like live. Okay, so we're kind of almost split. Okay, so there's more like live R. Okay. Okay, awesome. Even though this is recorded to you, okay. Okay, so why don't we, it sounds like, and I know not everyone has responded, so we have like a sample of our population, right? It sounds like live R probably will be most helpful. Okay, so I will record lectures and then just kind of continuously apologize, that they're, I don't know, hopefully not the most, okay, you like live lecture, okay. So the nice thing is with either format, we'll still have a live component of both. It's just sort of a matter of how much time do we spend, doing R versus doing lectures. So I can record the lectures and then have a much shorter mini summary of those, the recorded lecture. Oh, okay. So when you open up file, if you go to file, new file, and then R Markdown, if you click that, R will tell you if you need packages to be installed. So if you don't get a pop-up saying, you need updated versions of these packages, then you're good. You've got everything you need. So you should be okay. Okay, so we'll stick to the current format of recorded lectures. We'll have a mini lecture at the start, and then we'll work on R. And then later on, when we start to work on exercises, they're kind of like word problems. And so you'll see, what we're asking you to do. And then, I can I'll also be posting example code. And then you can take both of those and then work on your own. So, and I think there must be a way for me to allow students to share their screens or to create breakout rooms. And so if you decide, you want to maybe collaborate with other students in smaller groups, and work on the exercises together, you can do that too. So, okay. So for now, we'll stick to the current format. Okay, so now if you look on your Getting Familiar with R, you'll see now that everyone's loaded, you have a template. So this is really nice. This is actually pretty new to me too, because I'm used to using just regular R. But this nice thing with R Markdown is it's giving you a template for your code or for your script, which is really, really nice. So I will probably start doing this myself. Okay, so notice the title up here is shown on line 1, and that's what you named your file. And since it's a new file, it's currently untitled. So the other thing that's really cool about R Markdown is it lets you weave together plain text and R code, and that code is embedded in R code chunks. Okay, so you see these like 3 ticks, so these are all like chunks. Okay. And then if you remember from my video, I talked about comments, so commenting out text. So these hashtags, it just tells R, if you had just like a regular script open, it would tell you, don't run R. This is just information for me. Okay, so is everyone okay so far? All right. So the beginning set of ticks includes an R to denote the R code, and then an optional title. Okay, so if you want, you can include a title that comes after the R. So for example, like you want to write, I don't know, in the exercise, this is what it says. So let's see, oops, there, okay. So is everyone good so far? And then let me delete that, all right. Okay. So read the text in the practice script you just created. All right. So it's a Markdown document. Okay, this is great. All right. When you click knit, a document will be generated that includes both content as well as the output of any embedded R code chunks within the document. Okay. So the next thing on this, it says push the button labeled knit on the top of the script. So let's find that up here. And that's pretty cute. It has yarn and needles. So let's go ahead and click that. Okay, awesome. And I am going to save this. I'm going to save it to R code. So you can create a folder where you want to save your test code. And I'm going to name mine. Can everyone still see this? Practice scripts. Okay.
Yes.
Okay, awesome. So that's where I'm going to save my practice script. And then you can see down here, it's creating that. Awesome. Okay. Okay. All right, so compare the file that is generated when you hit knit. So this is in that pop-up window with the script shown in the code editor. Okay. Oops. Okay. So I'm having technical issues. Okay. So if you look here, let's see, sorry. Let me make that smaller. I've got stuff in the way too. Sorry, I apologize. Let me just clear out my screen. Okay. All right, so read the text in the practice script that you just created. All right. Oh, sorry. Let me go back down. Push the, okay. Sorry, I'm just going through the exercise with you. Okay. So this is what we get. Did everyone get this pop-up? Can everyone see that?
Dude, are you showing something?
Yeah, so maybe it's possible that you guys can only see our studio and not that pop-up that came up.
On share.
Okay.
It'll like zoom out and then it'll show like your whole screen.
Oh, okay. That you definitely don't want to do because I have like a million things open. Okay, but I see that like Megan got a pop-up. Okay, so I also got a pop-up. And so I just want to make sure everyone got that. Okay, awesome. Okay, so read the text.
I just want to make sure I got the right pop-up. Is it the one that says like untitled?
Yeah, it says untitled. And that's because like we, at the top here, see it's untitled. If you look at your script, there, okay. I've highlighted it here in my RStudio. It says untitled. And so that's why on our pop-up, we got untitled. And it's an HTML document. So you can see at the top of your pop-up, it should have the directory where this is saved. And then it has the extension HTML. Okay. All right. So now you can delete all of the code except for the header information. So you're going to delete lines 5 through 28 of the practice script. So I'm going to highlight all of that and delete it. Okay. All right. Now you can update the title of your file to report on wages. Okay. So go ahead and do that. Okay, then on line 6, so this, we're just going to give it some space to look neater. To calculate my monthly wage, I multiplied worked and multiplied this product by the number of weeks in a month. Okay, so I've typed that out. Let me just correct that. Okay, and once you've done that, now knit your file again. So hit that knit button. If you haven't finished typing it out, that's okay. Let's just click knit. Okay. And there you go. So here is your report on wages, right? It corresponds to the title that you've specified. It's an HTML document. Okay. And then at the top, you can see that it says exactly what you've written out. Okay. So the next thing you're going to do, so now I'm having trouble getting back into my RStudio. There you go. All right. Add a code chunk to the file at line 10. So I'm going to enter until I get to line 10. Okay. Then click the insert button. Okay. And choose R from the drop-down menu. All right. So you have your cursor here where you'd like to do this. Let me just, again, I'm having trouble with my mouse. Okay, there. Click the insert button and choose R from the drop-down menu. Hold on. Where is the insert button? Okay, so the shortcut for this option is Control-Alt-I on your PC. So I'm just going to do that. Okay, there. All right, so now you've created this new code chunk at line 10. So Control-Alt-I, and then I'm just going to pause there and make sure everyone's caught up. Okay, everyone good? All right, so now we're gonna go and do what we did down here in the console area. So we're gonna create the object monthly wage. Okay, and then write out our formula. So $25 an hour for 15 hours. The order is different here in this document, so I'll just put times 4 weeks, and then 0.8 to account for the fact that we get taxed 20%. Okay, and then name the code chunk calculate wage. So we'll go up to the brackets, and then we'll say calculate wage. Okay. So this is just a different way. You have these nice code chunks, and it actually looks visually a lot nicer than what I would typically do in R, which is just to have these hashtags to comment things out. And so this is exactly doing the same thing. You're basically documenting what your code below it is doing it. So that way, when you go back to your code, and again, sometimes our programs might have hundreds and hundreds of lines of code. It's a really good practice to kind of keep track of, okay, this section of code is doing this. Now this section of code is doing this. So this is just another way to do that. So it's just really a way to kind of organize yourself so that when you go back to your code, it's easy to follow. Okay. So now that we've done that, so on the next line, so still inside the code chunk, so this gray area, and I'm having trouble with my mouse again. Let me just pull it down. Okay, there we go. Okay, so on the next line inside the code chunk, right, monthly wage. Okay, so we're going to put our cursor at the end of the 8, and then we'll write monthly wage. Okay. Now execute the code chunk by pressing its green arrow or placing your cursor on the line of code and hitting Command Enter. Or on a PC, it would be Control Enter. Okay, so you're going to keep your cursor there, hit Control Enter. Oh, okay. Calculate is not recognized as an internal or external command. Let's just highlight our code, sorry. Let's highlight our code and then hit, and I'm still getting the same error. Let me try it this way. Okay. So I'm actually not sure what's going on.
Did you highlight both of them?
I did. Let me highlight one. Let me see. Interesting. Okay. I think what I'm going to do, so I apologize. So I'm working off of exercises that Dr. Armenta created, which are fantastic. But because I'm not familiar with R Markdown, I'm actually more familiar with just creating an R script from scratch and not having these like constant pop-ups. I might kind of modify these exercises to just work within the script that we've created from scratch. So I think I'll go back and modify these because this isn't helpful, right? When I'm trying to show you an example and I can't even do them, that's not very helpful for you guys. So So I think what I'll do is probably stick with what I'm familiar with, and just have us create a script kind of from scratch. This is really nice, this R Markdown, because it is a little bit more, like it's a little bit more interactive. But in terms of R coding and actually accomplishing what you need to do for your analyses, it really won't make a difference either way. So I think I'll modify maybe these exercises so that we're just working in the, in a script that we create. So for example, in that case, instead of something like this, we would have, these hashtags where we're commenting out that information. Let me just try something really quick.
I got mine to run.
Did you? Okay, so might be something with my computer.
Well, I left where it says calculate wage inside of like the little brackets. I left the R there with the space between R and calculate.
Okay.
And then I just highlighted the 25 times 15 and then I hit run. Yeah. And then the run.
Okay, awesome.
And then select. Yeah.
Okay. So maybe if we run this whole thing, that should actually work. Okay. So now that did actually run. Okay, awesome. So it looks like keeping this R here is essential. Thank you, I appreciate that. Okay. So the rest of the exercise really is just kind of a description or like a recap of the rest of, the environment. So here now, because we have a script open, we have our source code, our source area here, and then our console is down here. Okay, so I've just opened up the console there. And then we have sort of right now, our current environment. So we have our object that we created, monthly wages, with its value. And then here it's just kind of where I have, so this is actually all the Zoom lectures. And then here's the folder where I'm working from for this current exercise. So I guess I should ask, like, I can familiarize myself with R Markdown. That's not a problem if you guys want to continue to use this format, or we can just work from a script. So I don't know, is there a preference from you guys?
Is working from the script is like the bottom as opposed to the
no, that's the console. So let me give you an example. So again, like my mouse keeps getting hold on one sec. Oh, interesting. Okay, sorry, I'm having, okay, so let's see. Okay, so if I were to go to file, new file, and then I'm going to open an R script. So this is what I typically would do. So do you see that it's blank? And so if I wanted to run the same thing, I would do something like, okay, I'm going to comment out the rest of what this line is saying. I am calculating. Okay, and then I would have, sorry, monthly wage, 15 times, or sorry, $25 an hour times 15 hours a week, 4 weeks. So it looks very similar. And the only difference then to me is that, we are creating our own, you see how it's not color coded, but this is just this is a script. So, and then we just don't have this sort of interactive window on the right-hand side. But we can still, for example, like highlight this code, and we really don't have to highlight the commented out values and still run it. Sorry, there. So you can see it being run below. So the output comes out down here instead of like up here where we saw in our markdown. So there, I mean, it's a slight difference, but in terms of coding and organizing all of your code, it still is very similar. So I could still write this out, for example, in my R scripts if I wanted to. And I would just precede it with a hashtag so that it's there, so that it's all commented out, and R would know not to run those lines. It would give me an error anyway if I tried to run this. So that would be the difference. Okay, so no preference. So it sounds like maybe no preference. What I'll do, okay. So it would be good. I wish I had more time to like before this start to prepare for this class, to learn R Markdown and get comfortable with it so that you're actually not watching me make mistakes. But I think I will be more useful to all of you if I stick with something I'm comfortable with. So I'll just stick with the R script. And then we'll just actively, kind of document our code, and we can create chunks of code. We can still highlight it and run our code. When we start to do histograms, for example, so figures, we can still highlight the code that we're interested in, run that line, run those lines of code and create a histogram that will pop up. So give us a pop-up window showing us the histogram. So very, very similar. I think R Markdown is really, it looks really cool. It's just a bit more interactive. So yeah, okay. I appreciate everybody's flexibility. All right, so we'll use a script. So I'll modify the exercises a little bit so that they kind of are better examples using a script rather than this R Markdown file. So okay, so that's actually the end of our getting familiar with R exercise. You can just read the rest on your own. It's just sort of describing the rest of the environment, but it's nothing new. It's everything you've heard before in lecture. What I will do is then probably post a recording of lecture 3 later this week. And then we'll have a mini lecture on next Tuesday, and then we'll dive into a more complicated exercise. So complicated just meaning, I think that first exercise has maybe 5 or 6 different problems, and they're all just word problems. And then you will just read through them, and then I'll kind of guide you. So for example, the word problem might, I can't off the top of my head, it might be asking you to calculate or, describe your data, the, measures of central tendency and variability. And so then that what you need to do is calculate the mean, maybe the median and mode as well. And then, calculate standard deviation, for example. So we'll work through those. And typically those exercises that we start next week, they're longer. So we won't finish an entire exercise in one session. It might take us 2 or 3 sessions. And then, as I mentioned in the first class, if you don't finish the exercise, if we don't finish it in class together, then I would ask you to finish it on your own time at home. And then all of those exercises, all of that work that you do, you will submit to me, but they're not graded. So I'm actually glad this all happened with R Markdown, because as you can see, I tried to run something and it didn't run. I got an error, and it was a quick little fix where I put the R back and within the brackets. And so that is, very typical of, coding day to day. So I, even at work, something might not run, and then I have to go through my code and figure out why. And in the particular programming language I use, often it's because I've forgotten something as small as like a semicolon. So, so this is just very normal. So, it's a huge reason why, when you submit your code and the completed exercises, I'll go over them for content and effort, but I don't want to grade your actual code, so the accuracy of your code, because, throughout, if you continue to do this for the remainder of your careers, everyone's going to be making mistakes in their code. So that's very normal. So that will be kind of be the format then for the following week. And I think next week, the lecture will cover visualizing our data. So we'll probably start to really talk more in detail about scatter plots, histograms, box plots, and those sorts of things to really kind of characterize our sample data. So so that's all I had for today, actually. If anyone has any questions, feel free to ask, and I can try to address them. Okay, so no questions. All right, I will also post my email address onto courses so that you guys can reach out to me, since the CSUSM email does not work currently. And then if you would like to meet on Friday for office hours, please just reach out to me, and then we can set up a time to meet between the 9 and 11 a.m. on Friday, or if another time is better for you, we can also arrange for that too. So, oh, okay. So this particular exercise, getting familiar with R, you don't need to turn it in. Starting next week, I'll have exercises that are longer. They might be like 5 or 6 different things that we will work through during class. I'm not going to actually do the entire exercise on my screen. It's really, I'm going to sort of introduce the exercises, give you an idea of what you might need to do in R, and also I will post example code that you will use to analyze the data that you need to for those exercises. So largely we'll be working on them in class, yeah. And then if you don't finish them, then you do them at home, you complete them, and then you'll turn them in. And I'll let you know, week to week, okay, next week, could you please turn in, exercise 1. And then again, they're not graded, but I just want to kind of make sure, you're following along with the coding, and I'm able to give you guys feedback on your coding. Okay, sound good? All right, thank you. Good. I appreciate everyone's patience. I promise it will get, well, I hope, I can't promise. I hope it will get better over time. And great, you got RStudio, Amanda. That's awesome. Okay, awesome. All right, thank you so much. Have a great week, and I will see you guys next Tuesday.
Wait, I have a question.
Oh yeah, sure.
So I have a question on like, just I guess the coding, because a lot of the coding like of what to do already like on the internet and stuff like that. So are we able to like code? I don't even know what I'm trying to say. Like essentially, like I have like a list of codes that we'll probably use. Could we just put it like in the script and click Control R to run it? And it's like that simple?
Yeah, it's pretty simple. So, and that's oftentimes I think what everyone starting out will do, right? So you've Googled the code and found it, and I will also be posting example code, right? So, and most likely my example code is going to be very similar to the code that you found Googling. So yes, absolutely. Like if, if you're like, and so that's great. I'm so glad, like that's super proactive of you. So if you're, if you have code and you're finding like, let's say in class, I want you to, plot a histogram and you have code for that, awesome, you're all set. You just need to, copy and paste that into your script and then run it. So yeah, really? Yeah.
Holy smokes.
Oh. Obviously, right? There's a few steps where like you're pulling in your own data, so the code, you might have to modify that code. Specific to your data, and maybe let's say for a histogram, you want your X values to range from 0 to 20, whereas the example code, the X values range from 10 to 50. So those are the types of things where you would modify the argument within the function, the histogram function, and then that would give you the histogram that you want. So yeah, but if it, if you find something and it's like, how do I plot a histogram? And they tell you, okay, well, it's just, this function and this set of arguments, absolutely. You're just going to copy that into your script, modify it as needed, and then run it. So yeah, it is definitely pretty straightforward. So.
Oh, that's awesome.
Yeah, awesome. Okay, great. I'm glad you're excited.
That's so good. Thank you so much.
Okay. All right. Thank you, all of you. Have a great rest of your week.
Dr. Masunu.
Yes.
So I just want to let you know, I coach